Hello and welcome to part 8 of our quick run through electric and magnetic field theory. This time looking at an application of the results that we've derived so far, the parallel plate capacitor. Last time we derived an expression for the force on a unit charge, a distance above a uniform charge density plate. And we found that the force was independent of the distance above the plate and was equal to rho over 2 epsilon naught, where rho is the charge density of the plate. Right, that's just a single plate. What happens if we have two plates? Both infinite plates. One has a positive charge density and the other one has a negative charge density. And the two charge densities are equal in the sense that this charge density is plus rho coulombs per meter squared and this plate has a charge density of minus rho coulombs per meter squared. What is the total force on a particle now? Well, the total force due to this top plate is just rho over 2 epsilon naught, but the total force due to this bottom plate will be minus rho over 2 epsilon naught. It will be a force of attraction because this is a negative charge density. It will be being pulled down towards this plate, but being pushed up away from this plate. But since the force is not a function of the distance away from the plates, the force is equal and opposite in this case. Net result, the force would be 0. There is no force on a unit charge outside these two plates, which means there are no lines of flux outside these two plates either. All the lines of flux will be going directly from the top plate and ending on the negative charges on the bottom plate. What if the charge moved down in between the two plates? Well, if the charge was here, it would be being pushed down by the top plate, so there would be force on it downwards from the charges on the top plate of rho over 2 epsilon naught, and it would also be experiencing a force down because it's attracted to the negative charges on the bottom plate. So now these two forces would add up. They're both acting in the same direction, and the net force on a unit charge between the two plates would be rho over epsilon naught. So that's the field strength between the two plates, the force on a unit charge. Now the field strength is the force on a unit charge. If we consider how much energy it would take to move a unit charge from the top plate to the bottom plate, it would be the field strength times the distance. That just comes from the formula work equals force times distance. The field strength is the force on a unit charge. The distance is the distance between the two plates, which I've labelled here as d. So that would be the amount of work required to move a unit charge from one plate to the other. But the amount of energy required to move a unit charge from one place to another is, by definition, the potential difference between these 2 points. So this tells us that the potential difference, the voltage between these 2 plates, is just rho d over epsilon naught. Now, because we can't make infinite plates in practice, let's consider that the plates are not infinite. They just have a very large area A. or at least the area is very large compared to the distance between them. That would mean that the total charge on the plates is given by, I'll call it Q, rho times A. And from this equation here, I can see that rho is equal to epsilon naught V over D, and substituting this into there gives me Q equals epsilon naught A over D times V. These are all constants after I've built my capacitor. Epsilon naught, the permittivity, A is the area of these large plates, D is the small distance in between them. Q is the charge that I have on this plate, or the negative charge that I have on this plate. V is the potential difference between them. Normally, for a capacitor, I would define its capacitance in farads as being the ratio of the charge on one of the plates divided by the voltage. So I can see by comparing these two formulas that the capacitance of this parallel plate capacitor is epsilon naught A over D. And I can use these techniques of flux and Gauss's law to produce a very useful result to calculate the capacitance of this arrangement of two parallel plates. I could go further and I can derive another very useful equation from this arrangement of two parallel plates. I can derive an expression for the energy density stored in an electric field. And it goes like this. How much energy is required to pull these two plates a small distance dr further apart? Well, consider one of the plates here and consider a small area of the other plate. Call that delta A. We know that the force due to the charge, the negative charge on this plate, on a small charge in that region there, delta A, is given by the field strength at this point due to all these charges. And the field strength due to all these charges is just rho over 2 epsilon naught. That's the field strength away from an infinite plate of uniform charge. If I multiply that field strength by the charge in this small area delta A, that would give me the force on that small part of the top plate. Rho squared delta A over 2 epsilon naught. Now, the energy required to move this plate a little bit further away is the force times the distance. This is the force. We just have to multiply it by the distance. Because this is a positive charged plate, there is an electrostatic force of attraction between them. So I'm going to have to put energy into this system if I want to move these plates further apart. And the energy that I have to put in is the force, rho squared delta A over 2 epsilon naught, times the distance. In this case, just a small amount of distance, delta R. That's the energy to move delta R apart. Or the energy to move a small area delta A, delta R apart. You'll notice that the force here is not a function of the distance the two plates are apart. So I could work out the total energy that I have to put in to move this charge here from directly on top of this plate to this distance away, a distance d away from the plate, by just taking the force and multiplying it by the distance. That's just energy equals force times distance again. Or work equals force times distance. Energy and work, really the same thing. If you're losing energy, you're doing work. This work that I'm having to do, that is putting the energy into the electric field. So that's the energy that's being gained by the electric field. And that would be just rho squared delta A divided by 2 epsilon naught times d. That's just for this small amount of area, delta A. If I consider the whole area of the plate here, then the total energy that I would have to put in to move the plates apart would just be equal to the energy required per unit area times the total area. Well, the energy required to move per unit area is rho squared d over 2 epsilon naught. I just take the energy required to move this area delta A and divide by delta A. That gives me the energy per unit area. Multiply the energy per unit area by the total area of the plates, and I end up with this expression. Rho squared times d, the distance apart, times A, the area of the plates, divided by 2 epsilon naught. Almost there. Have to remember that we calculated the electric field strength between the two plates to be rho over epsilon naught. And we have to notice that d, the distance between the plates, times A, the total area of the plates, that's just the volume enclosed by the plates. That's the volume in which this electric field exists. I could call that V, volume. I've used V for voltage, that's confusing. I'll call it just vol for volume, is D times A. Right, substitute that into here and this into here, and we end up the total energy that I've had to lose to move these two plates apart. That's the total work that I've had to do, and therefore the energy that is now stored in the electric field. That's given by epsilon naught times the electric field strength squared times the volume divided by 2. I could therefore say that the energy per unit volume stored in this electric field is epsilon naught times the electric field strength divided by 2. And that is a general formula for the energy stored in an electric field. Epsilon naught E squared over 2.